Okay, let's not do Donald's idea. All right, so we want to do number 37 out of the chapter 14 review. We want to find the gradient of a function. Okay. How many variables does this function take as an input?
2.
2?
Yeah.
So what's the nabla mean in this?
F of S and F of T.
Yeah, so this guy, remember, right, is a vector. And in this case, it means partial with respect to S and partial with respect to T. Why am I doing S first and then T? Where does that?
Because it's defined as F, S, and T.
Yeah.
Perfect. That ordering's right here. You see that? Okay, so I'm going to do, what kind of multiplication is happening in here?
Scale.
Good. Okay, so to write this down in our kind of end of class notation, right? I'm doing the vector partial with respect to S, comma, partial with respect to T, and I'm scalar multiplying by the formula for F. And so that's 1 over the square root of S times T squared minus 2T plus 4. And on this one, I probably don't want to distribute. Why?
It's already broken out.
Yeah, because this is broken up nicely, right? So if I do this scalar multiplication, right, this guy's going to have to go into both bits. Oops, scalar. I'm going to get a vector, right? And it's going to be partial with respect to S of all of 1 over the square root of S times the quantity T squared minus 2T plus 4, comma, the partial with respect to T of what? Perfect. The formula for F again. And I realize I'm kind of overkilling this right now. But I want to highlight the similarities to the kind of curl and divergence things that we've recently learned, right? So what do I do here?
Partial derivative of S.
Yes. Right, differentiate. So partial derivative with respect to S, what's constant there?
The T squared minus T, 2T plus 4.
Good. All this stuff is constant, right? So that stuff's just going to hang out. So I've got a T squared minus 2T plus 4, just chilling. And then I need to differentiate with respect to S.
Yeah, it's going to be 2 over negative 2. Because you're going to have 1.
Let's see.
Negative.
It's been a long time for me. So I'm thinking this is S to the minus 1/2.
So negative 1 over 2 cube.
So I've got
Yeah, cube.
negative
Cube of
1/2
Cube root of that squared. Yeah.
S
times S to the
Negative 3 halves.
negative 3/2.
Yeah.
Just ignore what cube or whatever kind of root it is.
Yeah, don't try to simplify too much at once, right? You're already doing something kind of complicated, right? Taking a partial derivative. Don't overcomplicate it and try to do a bunch of simplification in your head. You'll lose something someplace. Okay, and then I got a comma, and now what's constant with respect to T?
1 over the square root of S.
Good, 1 over square root of S is constant, so that thing's just going to chill. We got 1 over square root of S, and then times
And then do the derivative.
2T minus 2.
2T minus 2. Perfect.
There's your gradient.
Okay, so my gradient of F, the thing I was looking for, is the vector given by this jazz, right?
Yep.
Okay, so depending on what you need to use this for,
You can evaluate.
simplify or evaluate or whatever. I'm just going to write it down, I don't know, minus T squared plus 2T minus 4 over 2S What was the power on S?
To 3/2.
So,
Square root of, so yeah, it's square root of, okay.
3/2. That's the square root of S cubed, right? But who cares? Comma, and then maybe on the second one, I'm gonna leave it exactly as it is. 1 over the square root of S times 2t minus 2. What's the gradient tell you?
How steep, or the steepest
Where it's
point?
pointing uphill,
Yeah, this thing points towards the steepest,
point on the contour 0.
yeah, it's towards the steepest
Steepest slope.
uphill, right? So if I put an S and a T in here, right, that's talking about a point in the domain, this vector is gonna point uphill from there,
Yeah.
right, towards the steepest spot you can go.
So
Where's the-
0, 0 would be the steepest point from the origin.
Yeah, so if I plug in 0, I get
Other than it going to,
undefined here, right? You guys see that? So what does that mean in terms of the origin?
done.
It doesn't exist.
There's an asymptote somewhere.
Yeah, there's some kind of an asymptote or a point of
Oh.
non-differentiability or something going on there. You guys see that?
And
Okay.
we could also take this and do a slope field.
Yeah, we could take this, we could draw a slope field for the gradient, right? We could, what else can we do with a vector field?
In the slope field, we would just be picking quarters of the box and figuring out what direction the slope is going at that.
Yeah,
point.
you just throw some random
make
points
that.
into this and
Okay.
figure out where it points. Yeah. I may make note that at S is 0, you have problems. Right, so I'd take that axis and dash it or something. Cool, questions on gradient?
So how would you find like the max point using that again? You set it to 0?
Perfect, yeah, so if I'm looking for a local max or local min, right? I set both components equal to 0 and solve.
Yeah. But in this
And
case-
then I need it to be simultaneously satisfied, right? I
we
need
do an
both
example of
partials
this?
to be 0. Yeah, sure. So,
What's this?
It'd be a bit hard, but okay.
This one kind of works.
no, this will work.
Zero.
So let's try an example. Let's see if we can set this thing equal to 0 and solve. Let me do this.